Okay, in this case, we're going to express in summation notation. So this time they gave us the values of our sum, and we're going to work backwards to give summation notation. So first of all, let's determine what's the difference here. 1 plus what gives you 5? 4. So we're going to determine if there's a common difference here that's added each time. So we'll have, whoops. And then to get from 13 to 17, we add 4. So basically each time we add 4, or if you looked at it in the reverse, the difference was to subtract 4 to get to the next term. So um, when we have this, we're going to have 4k plus a is going to be what we're going to use to determine what our k is. And the reason why 4 is the coefficient of the summation variable, because each of these, we found that to be how we got to the next, a common difference of 4. So let's do when our first term is equal to 1. So we'll say when k is equal to 1. So if we plug this into our formula, so this is going to be 4k, plug in 1, plus a. So we need to know what a is in our formula. So we'll have 4 plus a is equal to 1. Our first term is equal to 1 right there. Okay, so a is going to be what? Let's subtract 4 from each side. So a is equal to -3. When we rewrite this in summation notation, and this is the very first one, so we'll become a little more familiar with this as we go. So we'll have k is equal to 1. It ends, remember this value up here was how many terms we have. How many terms do we have in this particular problem? 1, 2, 3, 4, 5 of them. So this tells us the number of terms. Let me make a note of that. That's our number of terms. And our format over here is going to be the 4k plus a, but what did we find our a to be? -3. Now we can work backwards and check this if you'd like. So you can plug in, actually do the sum to this and see if you get this exact values. Okay, let's see another one. Just the more of these you do, the better you'll get in practice, but we don't do a whole lot in this format. So first of all, let's just look at our numerator. So in the numerator, what's going on? How do you get from this first numerator to the next numerator, to the next one, to the next one? It looks like we have a +1. Okay, now let's look at the denominator and say what's going on. So how do we get from 2 to 5? +3, right? What about from 5 to 8? +3. 8 to 11? +3. So first of all, let's just determine how we get from one term to the next. So our numerator and then our denominator, if we're trying to figure out the numerator, when we're thinking summation notation, our numerator is just going to be k, right? Because it's going to go from 1 to 2 to 3 to 4. It's going to up 1 each time, and that's going to be our k. And this one, there's something else going on. It's not just going up by k, so we know it's going to be in that format of the something k plus a. Now, what's the something in front of the k? It's going to be a 3, right? Because we're talking about our denominator, because of the same reason that we let our coefficient in front of the k be 4 this time, because that's how we got to the next term. In this case, when we're looking at the denominator only, it's going to be 3k plus a. Now we got to figure out, we're going to say when k is equal to 1, just like we did before. So when k is equal to 1, we just start with the first term. So we will have 1 over 3 times 1 plus a is equal to, now what is the first term in our given expression? That should be equal to 1/2. Okay, and right here we would just cross multiply and solve. So this is just going to give us 2 times 1 is 2. And then I'm going to have 1 times the other side. So 3 times 1 is just 3 plus a. And we're solving for a. So we're going to get negative 1 is equal to a. So our summation is going to be when k goes from 1 to how many terms do we have total? 1, 2, 3, 4. This is going to be how many terms we have. It tells us how far to carry the summation out. Now, our formula for it is going to be what was in the numerator? K. And then what was our formula for the denominator? 3k plus a, but we found out a was what? Minus 1. So 3k minus 1. And what this tells us to do is to apply this formula from the values from when k is equal to 1, and you do it 4 times until you get all 4 terms. Okay, now we're going to move more into area, and we're going to start with definition 5.13. In your textbook, it's page 262. Okay, write this definition down, and I understand that you're probably not going to understand much of this at all, especially it's the epsilon delta version of it, but we're going to slowly work our way towards understanding exactly what this means. So I'm just going to ask you to trust me on it. Let's work with it. Basically what this is saying is that area is going to be the limit as our delta x approaches 0. Is the sum of the function. This is going to be area, remember, is like length times width or base times height. That's going to be exactly what these guys represent later. You might not see it for that now, and I'm also going to try to show some visuals of it. So hopefully this definition will become more familiar to you and reveal itself as we go forward. So for now, I'm just going to ask you to write it down as we work towards when we come down here. So the area is equal to the limit of this, and it means that for every epsilon greater than 0, there's a delta greater than 0, such that if it fits this inequality, then the area between the actual area and the area that we calculate using our information that we're going to learn is going to be within epsilon. So if we chose it to be really small, our epsilon to be really small, then we can make our actual area, our estimation of our area, very close to the actual area under the curve. And like I said, we're going to work with that. So let's just move forward and see some examples, and we'll come back to this eventually. Okay, so these are really bad examples of the drawings in your textbook, but if you want to look at the region, this is on page 260. This is the exact area under the curve. This is inscribed, which is figure 5.4, and this is a bad excuse of figure 5.6, but basically you can see inscribed, or if we drew our rectangles below the curve, you can see that if I found the area of each of these rectangles by length times width, because I can do that, it's going to be a little bit short. It's going to be short of the actual area in these gaps right here. You can see some gaps. So the area of my estimate here would be less than the actual. And in this particular case, these are above the curve. You can see that our area would basically be a little bit more. Our estimate using these rectangles would be a little bit more than this. But basically, the idea, if we look back, the area is the limit as delta x approaches 0. So these guys are delta x. So let's say if this has 1, 2, 3, 5, 6, 7, 8, 9 rectangles that are of area delta x. If I chose to let this delta x, this rectangle, to be even smaller, let's just say cut this in half, cut all of these in half, then you can see that my area is going to decrease. So as I want to make these smaller and smaller and smaller, what happens is this gap right here will be a smaller gap, so it's going to get closer and closer. So the more willing I'm allowing my delta x, which is my width of my rectangle, to get very, very small, the more accurate my area of the region will be. So the limit as delta x gets close to 0 of the sum will become very close to the actual area. So we're going to use this method in just a minute. Like I said, we're going to chip away at that definition as we go. So let's look at an example on this next video.